Shall we start now? It's 6 o'clock. Am I audible?
Yeah, you're audible, and I
Okay.
think we should start.
Yeah. So, good evening, all. Welcome you to the online workshop on undergraduate physics experiments. I hope you will enjoy this
Shall we start
workshop for these 3 days, and after that also we'll be in contact. Am I audible? If you want so.
Yeah, you're audible,
And
and
now
I think
may I
we should start.
request our senior most colleague, Dr. Pratibha Pal, Associate Professor, Department of Physics, Victoria Institution College, to deliver her welcome address. Pratibha.
Good evening, everyone. Members of the organizing committee of the workshop, Professor Gaur Prasad Das, President, Indian Association of Physics Teachers, Regional Council 15, Dr. Surojit Chakravarti, Convener, Dr. Shinjini Dasgupta, Co-Convener, other honorable members of IAPT Regional Council 15 present here, my colleagues, my dear students, and all other participants. On behalf of our Principal Madam, Dr. Nivedita Chakravarti, and the members of the organizing committee, it is my proud privilege to welcome you all to this online video workshop. This workshop has been organized to enhance the ability of the undergraduate physics students to perform experiments using some basic equipment. Our valuable speakers, Dr. Bhupathi Chakravarti, Dr. Surojit Chakravarti, Sri Shoumen Sarkar, Dr. Makhonlal Goswami, Sri Sanjay Pal, Sri Deepnarayan Ghosh, and Sri Swadesh Ranjan Bera will introduce to the students a few alternative methods of performing some basic experiments through demonstration and further discussion on each experiment. Let us hope this initiative from their end will actively engage the students all through the session and encourage them to learn physics through experiments. I hope our student participants deprived of regular classes in this pandemic period will largely be benefited from this workshop. I wish this workshop a great success and look forward to your active participation. Thank you all.
Yes. Thank you, Pratibha, for extending a warm welcome to everyone present here. Now I take the privilege to introduce Dr. Bhupathi Chakravarti to say a few words about IIT and to introduce him. Let me first introduce him. He taught physics first in Chakda College and then in City College. He is associated with the Indian Olympiad program that involves the selection and the training of the students for the international and Asian physics Olympiads. He was the General Secretary of Indian Association of Physics Teachers from 2013 to 2018. Dr. Chakraborty is a science communicator and regularly writes popular science articles and essays in Bangla and in English. Sir, now the stage is all yours.
Thank you, Dr. Dasgupta. A very good evening and namaskar to everybody. Now, first of all, I must communicate to all of you that the President of Indian Association of Physics Teachers Regional Council 15, Professor G.P. Das, got tied up into some very urgent work. At this point of time, he was expected to join us, but I believe he will be able to join us in the later part of the program, and I hope he will be able to speak before you around that time only. Now, for my part, I've been bestowed with the responsibility of giving a brief introduction about our organization, Indian Association of Physics Teachers. I believe the very name communicates the major thing that it's an organization for the physics teachers, and it actually came into being in 1984. So it is about 37 years old, having 8,000 plus like members. This organization was established thought about by or founded by Professor D.P. Khandelwal, along with some of his colleagues and friends. And Professor Khandelwal was a physics professor at Kanpur. Now, Professor Khandelwal was actually a visionary, and this year, 2021, happens to be a centenary year. And we, in Indian Association of Physics Teachers, are really trying to, I shouldn't say celebrate, but mark this centenary year in different ways, in spite of the restrictions imposed on us this pandemic condition. Professor Khandelwal was instrumental in proposing so many things, and some of them he could not finish, and we are carrying on his legacy. Now, IAPT actually is subdivided or decentralized in several regional councils, about 22 regional councils, and we here in West Bengal work under the Regional Council 15. We are having one monthly bulletin that comes out with articles mainly on physics teaching, physics learning, and physics education related areas, because in the very constitution of IIPT says the objective of IIPT is the betterment of physics teaching learning at every level. IIPT conducts the National Graduate Physics Examination. I believe you will, all undergraduate students will take interest in this particular program. And if you want to know more about all these things, you please visit the website of Indian Association.
Troubleshooting
It is indapt.org. We shall give you it in writing, don't worry. Now, just a few more words about this activities of this Regional Council 15. We really conduct one flagship workshop that has been proved to be of great impact for nearly last 23, 24 years. It is now known as C.K. Majumdar Memorial Summer Workshop in Experimental Physics. This is meant for the outgoing BSc Physics third year honor students. And for last several years, we are holding it in collaboration jointly with S.N. Bose National Center for Basic Sciences, Kolkata. And Professor Khandelwal was instrumental in establishing one open laboratory some 28 years back in Midnapur College, Midnapur. This is known as IIPT Midnapur College Center for Scientific Culture, or we popularly call it Center for Scientific Culture, or CSC. This concept is unique. It is like an open laboratory. In fact, you people, the students can always try out their ideas by going over there. And over last these 28 years, I must proudly tell you that large number of students have come and worked over here with their ideas. They have tried out the things experimentally, and good number of new experiments have been developed and emerged through their activities. Professor S.C. Samanta is a key person who, even after his retirement, worked tirelessly along with his colleagues like Dr. Goswami, Dr. Rajiv Pradhan, and of course, the principal of the college, Dr. Bera. All of them worked together to make this center a learning center and a unique center for the physics learning. Finally, I must tell you that we are holding this sort of workshops for the first year students or the second year students, particularly for the first year students, in different colleges for 3 days, and these were mostly experimental workshops. But as you can understand, because of this pandemic, we could not do it for the last 2 years. And in a way, I must admit, I must appreciate, first of all, our colleagues from the physics department of Victoria College for taking this initiative, because this particular workshop, so to speak, is an experiment for us also. So I'm curious to see what really comes up in next 3 days, and how you people, the students particularly, come up with their ideas and suggestions and their likings and dislikings, because that will really help us to plan for our future activities. With these words, and I thank all of you, and I really particularly thank my colleagues in the physics department of Victoria College. Thank you.
Thank you, sir, for intimating us about the key role played by the IAPT in physics education for so many years. Now, Dr. Surojit Chakravarti, convener of this workshop, will introduce to the motivation and different aspects of this workshop. First, let me introduce him to you. He has been teaching physics at Ramakrishna Mission Vidya Mandir, Belur Math as a guest faculty for the last 10 years. Before that, he served at Maharaja Monindra Chandra College for about 37 years. Dr. Chakravarti is a PhD in experimental high energy physics from the Tata Institute of Fundamental Research. He did his postdoctoral work in KEK, a high energy physics particle accelerator center in Japan. He has a number of publications in international journals in both experiment and theory. For the last 25 years, he has been engaged in developing experiments for students. He has published a number of papers in national and international journals on physics education. In one of his works published in an international journal, Dr. Chakravarti determined the viscosity of air. This was done completely at home. Dr. Chakravarti is a life member of IAPT and intimately associated with the International Olympiad Program of India, organized by the Homi Bhabha Center of Science Education, a wing of TIFO. He is also associated with the Asian Physics Olympiad Program organized by IAPT. Sir, over to you, sir.
Thank you, Dr. Dasgupta. Am I audible?
Yes.
Okay. For your kind introduction, thanks once again. Good evening, everybody. Sometime back, Dr. Dasgupta, head of the Department of Physics, Victoria Institution College, in a meeting of IAPT members, put forward a proposal for holding an online workshop on undergraduate physics experiments. Over a long period of time, members of IAPT have developed many experiments which can be done with equipment which is easily available and cheap. So we, the members of RC15 of IAPT, considered the proposal of Dr. Dasgupta and agreed. As a result, we are holding this workshop from today for 3 days. Our resource persons will discuss experiments at an introductory level, considering the fact that the first and second year students in different undergraduate colleges didn't have the opportunity of doing any experiments for close to 2 years. It should be made clear that we will discuss experiments which are not included in the syllabi, but are thematically close and have some novelty. We understand that students have suffered an irreparable loss of their college classes for the past 18 months and more. Though they have found some opportunity for attending theoretical classes online, practical classes have got the real beating. So we thought about this online workshop on experiments, hoping this would at least partly compensate the loss. We have designed the experiments in such a manner that they can all be performed from home with cheap equipment. We advise students to pay attention to the presentations by our resource persons. We do not expect students to perform all the experiments. They can select a few which they like most and purchase the required components from vendors who deal with scientific instruments. The idea of performing experiments at home may be new to the students. However, if they can arrange some basic equipment, for example, a convex lens, which doesn't cost more than 100 rupees, they can design many experiments. Of course, there are challenges which need to be overcome. In our presentations, we will show how we have overcome some of these challenges. I personally find great satisfaction in performing experiments at home. For some experiments, particularly electrical ones, students may have to depend on instruments like a digital multimeter from the college lab. Here, the cooperation of the teachers will be needed. At this point, I would like to thank Dr. Shinjini Dasgupta and her departmental colleagues for having put in enormous efforts in organizing this workshop. Nowadays, most students have a smartphone at their disposal. We'll demonstrate how this is a wonderful instrument for carrying out physics experiments. In fact, I would call a smartphone a physics lab in the palm. If you look at educational journals from Europe and America, you will find that many papers on experiments using the sensors inside the phones have been published during the pandemic. It is a pity that our students are not aware of this modern trend in physics education, particularly during this COVID time when students have been forced to stay at home. I hope students will be interested in home experiments in general and will help in developing a culture of home labs in days to come. Thank you all. Happy home experimenting. What do you, Dr. Dashgupta?
Thank you, sir. And I hope that the students must have been highly motivated by your words. And I also thank the members of IAPT. Without them, this workshop would not be possible. And last not but the least, I want to thank my departmental colleagues also. About just some I mean,
Logistics
how
second
yeah
session.
how yeah how I want to actually proceed in this workshop. Shortly, we will post a Google Drive link in the chat box of Google Meet, as well as in the YouTube chat box, where you will, if you click on that Google Drive link, you will find the materials uploaded by our respected resource persons. Some of the materials also uploaded later on. So you just save the link, you keep on checking, so you will get all the materials. So this material will actually help you in trying the experiments at home. And those who will attend this workshop for all 3 days, they will be included in a WhatsApp group on 2nd December evening, or maybe on 3rd December. And this WhatsApp group will remain active for another 15 days. So say up to say 17th or 18th December, this WhatsApp group will remain active, where you can access all the resource persons. So if you are trying those experiments at home, whatever the results you are getting, or if you're facing some difficulties, or you have any ideas, any suggestions, you can communicate over there. And I wish a grand success to this workshop. And now we move on to the technical session. Our resource person for the first technical session is Dr. Bhupathi Chakravarti. Sir will discuss how to measure Young's modulus of a steel ruler in the form of cantilever by method of flexure. Sir,
Okay.
yeah.
Thank you, Dr. Dasgupta. What I want to do, let me tell you, I want first to show a few things over here. Then I want to go for screen sharing. So
Okay, sir.
should I move like that?
Yeah, sure. And just one reminder, participants, please mute your microphone and do not switch on your video, and never ever present your screen. And if you have any queries, please type that in the chat box. At the end of each technical session, we will hold a question answer session. So don't worry, your questions will be answered. And as I can see that now already 90 participants are here in Google Meet. So from now on, we will not admit any participant in Google Meet. You are provided with the YouTube link, so you can move on there and you can see it in a live streaming. Thank you. Sir, you can start.
Thank you, Dr. Dasgupta. Dear students, I'm really going to talk about an experiment which is very much possible to perform at home. You won't need much material. Even whatever you will need, those are pretty inexpensive, and you can try them out. I'm going to talk about the determination of Young's modulus by using a cantilever. Have you heard about a cantilever? Possibly you know it. Cantilever is essentially like this. I'm using a wooden strip, but it can be a metallic one. Wooden strip I'm using because so that you can see it very easily. Now, what do we do with a wooden strip like this? We can use it for the determination of the Young's modulus of this material. Now, what is being done? Let me tell you. It is being clamped at one end. It can have other length on the other side. I'm showing it so that it is visible in the screen. I think you can see it. Dr. Dasgupta, you please guide me if anything is not visible. Okay. Now, if you really look at the free end, this is the free end, you can really use some weight over here and make it to depress like this. You can have some depression by putting weight over here. Or you can put some weight and allow it to oscillate like this. Of course, this oscillation is very fast. I shall tell you how to control it. Now, basically, with the help of a cantilever, you can do this experiment in what you call in two modes. One is known as statical mode, where you calculate this depression and try to calculate the Young's modulus. On the other mode is known as dynamical mode, where this oscillation takes place. Now, I'd like to just have a caveat on this, that basically what we are trying to do here is trying to have some sort of an estimation of the values of Y Young's modulus. I won't call it a determination because there are factors which you really cannot measure very accurately, but you will definitely get a flavor of the experiment. You will definitely get an order of magnitude answer. Now, what I'm really going to do, I shall show you some text material. Then once again, I come back to this mode, and then I shall show you some videos so that I can explain the things. To start with, I shall really begin with the experiment, which may be called dynamical method. Before that, what I'm trying to show you, I'm really holding this long wooden strip. Wooden strip, you know, this is easily available in the market. If you go to the people who are dealing with this wood, they give the strips, and in Bangla, this is quite often referred to as beat. These strips are used in the furniture and in other materials in the decoration purpose. If you go there and choose something which has got a lesser thickness, lesser depth, because this depth D, this vertical depth, this is important, you will find it soon on. And this one, this is the width, you know, this width also need to be smaller, but there are other considerations. You will soon realize that you will take very thin strip, it may break and there will be other issues. So you will have to be judicious. Now let me show you one thing before I go to the actual text. Now I'm holding the other end at a reasonably far end. I mean, this free end is about 1 meter long. Now, if you can see, if I really oscillate it like this, you will find the oscillations are not that fast, and you will be able to calculate the time period of oscillation. In any case, let me go over to the text by sharing the screen. Should I share the screen now?
No, sir, it's not still visible.
No, it's not. I'm really.
Yeah. Now it's coming here.
Okay. Is it visible now?
Yes, sir.
Okay. So first of all, as I told you, I'm going to explain you the dynamical method, where you will find the Young's modulus by the oscillation of the cantilever. Now you can see this is the cantilever. It has been fixed at this end, clamped at this end. By clamping, we mean in a laboratory we may use a G clamp, but here there are 2-3 ways. Number one, you can put glue tapes over there so that they remain firmly stuck with the table. Or I have tried out, I have put up some heavy books like dictionaries over there, and moreover, I have put my palm over there to press them so that this end remains rigid, and this end has been loaded with coins. Coins means, as you can see, I have used rupees 10 coins. Each rupees 10 coin is 7.6 to 7.7 gram. I have also used 7 rupees 5 coin, golden color. Those are lighted, 5.9 to 6 grams, and rupees 5 coin silver color, those are 8.9 to 9 grams. You can use them, and remember, you will have to load it on the both sides with the help of a sellotape. And if it will be very nice if you really put 50% of the coin outside the clamp, outside the cantilever, because in that case you are really putting it at the end. The diameter of the center of the coin is passing through the edge of the cantilever. I shall show you how it can be done. Now, I have already uploaded some text material for a very well-known, very classical book of physics practical by Wasnop and Flint. This is an old one, and The most of the experiments described there are not in the part of the UG curriculum, but this being a classic book, it is still being used as a reference book, particularly by the teachers. So you can have a look about the deductions and other things. I shall come straight away to the expression of the time period when it has been loaded like this. Now the time period is given by 4m. What is a small m? Small m is the load you have given here. Maybe 2 coins on 2 sides, I mean up and down, 2 surfaces of the cantilever, and you have used sellotape. Then you can increase the load. You can put 2 more coins on the 2 sides, identical coins, of course. Then if you want to increase 2 more coins on the 2 sides, this way we can go on changing the m. Now it depends on m. M is the load you have provided, and this capital M, 33 by 140 capital M. Capital M is very important. Capital M is the mass of this part, only the exposed part of the cantilever. Now how to get it? If you can, suppose you are having a 2 meter long metal strip or whatever you are having, wooden strip, metal strip, if you have, there are issues, I shall talk about them. Now if you really get the mass of the entire strip from a local shop, you know what is the mass per unit length. So when you are using length L as the oscillating part, this is the length L, only this part, the exposed part, you can find out capital M because you know the mass per unit length, multiply it by small m, you will get the capital M. And in downstairs we are having Young's modulus of the material Y. B, as I mentioned, B is the width of the scale or the strip, and D is very important, thickness. Now in this context, let me tell you, this thickness can really be reduced for metal strips like steel scales. But for wood, this D is rather thick. In any case, for the measurement of D, you should rely on the use of a screw gauge, which you can have from your college lab. So it's better you take a part of the sample strip with you to the college lab, get the D measured from there and use it in this experiment. So once again, I repeat, and then I shall be showing you some videos. This is time period to pi 4 into m loaded mass. M, mass of the oscillating part of the cantilever. L is the length of the cantilever. Y is the Young's modulus. B is the width. D is the thickness or depth. Now let me show you how it works, and particularly you will realize how we need to handle it. I'm going to show you a few videos. Now, first of all, let me show you one steel strip. You can have a look how it works. Or let me first show you a wooden strip, wooden scale. Look at the video, then I shall talk. You can see it is oscillating like this and it has been loaded at the end. Now, if you change the length, we have increased the length, and you can see the time period has significantly enhanced, and this time period is very much measurable. In fact, previous time period is also measurable. If it is more than 0.5 seconds, it can be measured. For the benefit of the viewers, I would like to show this once more. Have a look at it. So this is the way you need to really do it. Now I shall go to the next video where, as you can see, where we have used a steel scale. Steel strip, as you can see, is the advantage of the steel strip is that it can be pretty thin. D can be pretty thin. And you can see I have used a dictionary to hold it, to press it for clamping purpose, so that I can easily change the length. And I believe you have noticed one thing: when the loading is good, the entire mass has got more potential energy when deflected from the equilibrium position. So the kinetic energy takes time to decay out. And so this oscillation really goes on for a long time. You can easily take 30 oscillations and for the calculation of the time period. So that way it's quite convenient. And you can see the difference between the two stages when it is shorter and when it is longer. The time periods are significantly different. And now I shall come back once again to the text part, then I shall go back to the video again. Now, interestingly, if we really look at it, this time period, as you can see, depends on number of things. Among these, Y, B, and D, they remain fixed in a particular strip. You can change M, and if you change L, what will happen? This capital M will change because this is the part of the mass of the oscillating part. So let us do one thing. Let us first linearize this equation. I hope you can understand this is not a linear equation. If you try to plot T versus M, the equation will be quite complicated apparently. But by suitably choosing the variables and by squaring both sides, etc., we can get a linear equation when the plotting becomes easier. Now, what I have done, I have separated out these two parts, and what I have ultimately obtained, T square is equal to 4 pi square. Then the entire thing under the bracket that has come and have separated out, we get a relationship like this. You can see 4 pi square into 4 comes, this becomes 16 pi square m, etc. So 16 pi square L cube m by YB d cube. And the second part, that becomes 4 pi L square L cube 33 by 140 m by YB d cube. Now, if you really look at this relationship, so long you are not changing the length remains fixed, then m remains also fixed, capital M, because that is a part of the mass of the oscillating part, mass of the cantilever. So this entire equation, if you take T square as Y and this part, except the M, you take that part as M, that means the slope, into M as X. So it is Y is equal to MX. I mean, M is like X. Incidentally, the symbol has become like that. And this part is, of course, constant. So it is C. So if we have an arrangement where we can really go on changing the mass at the end, keeping, of course, the length fixed, so L cube remains the same, M remains the same, then, of course, we have an equation like we can linearize the equation. That means we can make the equation of a straight line in this way, so that if we plot T square versus M, we shall get a straight line where the slope will come from here. Okay. Of course, the intercept, that also involves Y, B, D, etc. We try to rely more on slope because the entire straight line may get shifted up or down because of some systematic error. In that case, slope will not change, but the intercept may change. So looking at the slope, you can really, from this slope, you can try to have an estimation of Y, because you know L, you have measured it with the help of a scale, the oscillating part. B, you have measured it maybe with the help of a slide calipers if you go to your college lab. And D, you have measured with the help of a screw gauge. So that will help you to get an idea about Y, estimation of Y. Now, I shall show you one more thing in this context that is very interesting. That is something, you see, I'll show you a video before I go to the next part, that is the experiment with in the static method. That means by measuring the depression. Now, I'd like to show you one interesting thing. I personally like this one. Look at it first carefully, then I shall talk about it. I hope you can see this oscillation is taking place, not in the vertical, it's not going up and down, but it is moving laterally. Can you see that? I'll show you again. Remember, you can have the experiment done this way also. This is because I hope you can understand that this oscillation is not controlled by the gravity. It is, if you really look at the expression for this expression, there is no presence of G, acceleration due to gravity over here. The oscillation takes place because of the elastic property of the cantilever. When we really depress it from the equilibrium position, essentially elastic forces come in to restore it back to the equilibrium position, And you know how this restoring force develops, and it really doesn't stop at the equilibrium position. It shoots up, goes to the other side, and the oscillation goes on. Of course, there are dampings from different sources, so after some time it stops. So this is very interesting to note. There is no G over here, and so you can have this experiment done either vertically, either allowing the oscillation to take place in the vertical plane or in the horizontal plane. Personally, I would like all of you to perform the experiment in both the ways and check what sort of things are happening. Of course, you will find the clamping will be a bit more difficult, maybe a bit more difficult for when you are allowing them to oscillate in the horizontal direction. Of course, if you are using glue tape, it's not be that problematic. Now, I shall show you one more interesting video, because you see what happens. I'm going to the next stage, and this is, first of all, let me show you this one. This is an unloaded scale, unloaded long strip of wood, and as you can see, without any mass, it can oscillate, because we know there are two parts in the equation. So it can really oscillate like this. And now, because there are two parts, even if this small mass, if small m is absent, because of capital M, we are having some loading, so we can still have a time period of oscillation. Wooden strips are very convenient, so to speak, but I have a word of caution. Number one, that it has got much lower Young's modulus, about 9 to 10 gigapascal, 9 to 11 gigapascal, whereas your steel is having 200 gigapascal. By gigapascal, you know, I mean 10 to the power 9 Newton per meter square. So in steel, you can shift it and get it 20 into 10 to the power 10 Newton per meter square. But as I have told, in steel, D may be quite thinner, and of course, you can take suitable aluminum strips, and I'd like to show you. Sometimes aluminum strips, if you don't take it, the way I have got one, this is, I mean, this shows huge bending. You can show this has got some kink also, but time period is very reasonable, very reasonable. Particularly if you really increase the length, you will find now the length has been increased. The bending is too much, but the time period is manageable. But when it oscillates like this, some vibration comes in, some lateral vibration takes place. So it's better not to go for so much of depression, and you will have to, because this is pretty thin, this aluminum, and you will have to choose a suitable strip that way. You can go to the hardware shop, you will get these aluminum strips, and you can really procure one from there. Now, I'm really going to the second part for the depression calculation. So my suggestion would be, let me sum up over here before I go to the second part. You take the data of time period by changing m, small m, that is loading, keeping L fixed, because that will change capital M. So for one particular length L, if you take several m and corresponding t square, you can always draw a graph. And I'd like to highlight the utility or the importance of drawing graph with this data, because in that case, you will be able to see whether the data are consistent. Some of the graphs, if you find the graphs are, I mean, expected to be in straight line, if you find, say, 3-4 points have come very well over a straight line, 4th, 5th and 6th point have gone wayward, then you know that those points are really not right, and you will need to repeat those data and that sort of things. So it's always better if you can draw a graph with the data you have collected. You can have a more reliable outcome in the experiment. Now, I'd like to go to the second part. Second part, once again, it's a cantilever, but it's a method of statistical method, as we call it, by the method of depression. I believe you can understand that this depression of the free end, if you go on loading, it will get depressed. So in a way, if you're really putting on mass m at the end, it will go on depressing. Of course, it's a simplified formula. We have ignored the mass of the strip. If the mass of the strip has to be taken into account, we need to add some additional terms. I have not shown it over here. Now, basically, principle is that you go on, you keep one string or any reference line attached. Say you can really put a string from one window pane to the other side, and initially the horizontal level of the strip should be along with the string, and once it gets depressed, you can measure this change. This is in the diagram, this is delta, this is actually y0. This, you can measure this depression with the help of a scale. So each time you load it with m and go on changing, you will get depression, and then you change m and you will get depression. If you are really using a wooden stick, the contribution from the mass of the beam is not much, because wood is very light, density is much smaller. So m is a fairly good approximation. But of course, if you're taking metal strips, then this metal strip will have contribution. I hope you can understand this entire string. I mean, if you really consider the entire length, the mass contribution from this cantilever will depend on the length. And one more interesting thing is that since we are loading it at this end, this loading means we are applying a force, and elastic forces develop internally and they try to take it back. So you can understand, I mean, this external force is trying to bend it about the point A, and internal forces develop due to elasticity that is trying to take it back to its original equilibrium position AB. Now you can understand one thing, because we are loading like this, G has come over here. Of course, G is there. So acceleration due to gravity is there. So I can tell you that, well, depending on the G, this Y0 will change, of course. But G has got only the role that we have wanted to apply this force. Had there been any other suitable method by keeping it horizontally, if we could have applied some suitably known force, we could possibly do the experiment in the same way. But it's much more convenient to put some mass over there so that the weight acts like this and comes up with this expression. Once again, you can see YB dq is downstairs. So Y is the Young's modulus, B, as you know, this is the width, and D is the depth. Once again, D and B has to be measured properly, D with a screw gauge and B preferably with a slide calipers. M mass, of course, we can once again add this 10 rupee coin, 5 rupee coin, whatever may be the case. So here, of course, you can draw a graph, approximate one. You can, in fact, that approximate graph will tell you, if you really ignore the weight of the cantilever, what sort of graph you will get. Y0 versus M graph, that is expected to be a linear. If there is much deviation from the linearity, then we will have to admit that we are taking into consideration the weight of the cantilever beam. You can try it out. That formula is given over there. But basically, this is the principle. And I shall now switch over. I mean, I shall stop sharing the screen, and I shall show you one or two things with the help of the wooden strip at my disposal. So should I move out? Dr. Dasgupta, should I move out from screen
Yeah,
share?
sure, sir. Yeah, yes. It's as per your choice.
Okay. So I stopped sharing, but I shall show you a few more things. Okay, fine. Thank you. And now I wanted to show you this thing. If you take one coin, suppose I am having a coin. I forgot to bring one coin with me. Or anyway, look at this coin. There's one 5 rupee coin. Now, what I was suggesting, that if you are loading it with the help of this coin, don't put it like this. You put it like this. Keep the diameter. The 50% of the coin should be at the edge. I don't know how far it is visible. I'm trying to show it in this way. So don't put it like this. You put it like this. Do you get my point? Or you can have a look. Put it like this. Put it like this. 50% will be outside, so that it really gets loaded at the end. And whenever you are putting something like this, you will have to put the similar coin on the other side, so that it gets uniformly loaded and systematically loaded. So I have not talked about the measurement of time period. Had it been our student days, we would have really much bothered about the stopwatch. Now nobody is bothered about stopwatch. It is a very much within, mobile phone and other parameters I have talked about. You can get them really measured very easily. And my suggestion would be, even if you can take two things. One, I have used this steel scale, which is 2 feet long, 60 centimeter long. This is available in the market. It costs about 70, 80, 90 rupees depending on the shop. You can have one scale that can be used for other purposes also. That scale gives you good oscillation. If you keep it, it's a 60 centimeter. If you keep some 45 centimeter, then even 50 or 55 centimeter, then you will get excellent results. If you go on putting the 10 rupee coins, several 10 rupee coins or several 5 rupee coins. And of course, you can use this, what you have told you, that's beat. I don't know the exact counterpart, wooden strip essentially. These are known as beats in Bangla. You can use them, and you can have. I believe you will have a good result. And you can consult any textbook. This, depending on the nature of the wood, there are several types of wood. The Young's modulus vary from wood to wood, so there is a range in the values of the Young's modulus. So basically, this is the idea. What I'm really going to do, I shall put the text material that I've discussed. That's a 2-page material that I shall put that material over the this thing in the Google Classroom. I shall upload them, and if you wish, I can put on a couple of videos also. So I think I have come to an end. This is something I wanted to really talk about, and of course, as Dr. Dasgupta suggested, you can really communicate me, but please try and then communicate. Don't, before trying anything, please don't start writing me. Please try out something. Come up with your photographs. No, not videos. Videos are large. It's difficult to send them by email. You come up with your photographs, show me the arrangement, and of course, I'm not only interested to listen about your difficulties, but I'm really very much eager to listen about your success, how you are getting the things really the right way. I think you will be able to do it, and if you really try it out, and if possible, try to do it along with one of your friends. That will be convenient. This clamping business and other things, so many things are there. So if you really have a lab partner, so to speak, I think these things will be better. So let me stop over here. I think I should not elongate it, prolong it anymore. So thank you. Thank you for patient hearing. Dr. Dasgupta, now it's over.
Yes.
Thank you.
Thank you, sir, for your nice presentations. Hope that students will try it at their home. And whatever material you want to upload, you can upload in the Google Drive. The link of the Google Drive is already shared in the chat box. I will share it again. So you just save it, and once you will open there, you will find a folder named after Dr. Bhupathi Chakravarti sir. There you can find his materials. For every resource person, there will be a separate folder, but I'm sharing you the link of the master folder, so you can access it anytime. And as I said, that later on, once you are attending the workshop, and since you know that tomorrow we will have another program, and then the next will be on 2nd December, so you will have some time. So once you are trying out these experiments at home, we will create the WhatsApp group, so you can communicate with the resource persons over there. You can post your results, your queries, or any new ideas. And now the question and answer session will be conducted by our departmental colleague, Dr. Shubhendru Chandra. Shubhendru, any question?
No question, no technical question has been arised, but one question of the Google, about the Google Classroom. How we will access the Google Classroom?
No, it's basically they will get the materials in the Google Drive, and if someone is interested, then we can add them to the Google Classroom, but that will be done later on, not at this moment. And is there any question in?
No question.
No. Also in YouTube Live, there is no question. So thank you very much, sir. I hope they will communicate also later on, because first they have to try it by themselves. Then only they will find the difficulties. Also, they will get the actually the also essence of the experiment, because also they will enjoy once. Only they will try by themselves.
I mean, as it is said in Hindi, मैदान में उतार के पहले कुछ करना पड़ेगा.
Right. That's it. Okay.
Thank you.
So we are moving on to the next technical session. Our resource person for this session is Shoumen Sharkar. He is an assistant teacher of physics at Karui PC High School, Hooghly, West Bengal. He is interested in designing new experiments in physics, and he's also author of a number of new experiments published in international journals of physics education. Now he will explain you how to measure the focal length of a biconvex lens, focal length of a concave lens. So basically he will be explaining a few experiments with the lenses, and also he along with Dr. Surajit Chakravarti, they will actually continue the next two technical sessions, the different experiments with lenses. So now Shoumen sir and Surajit sir, stage is all yours.
Thank you, ma'am, for your kind introduction. Now I am sharing my screen. Good evening, everybody. Now we will discuss some experiment using lens. First one is to determine the focal length of a biconvex lens by UV method. And here actually we are using the material that is available at home or nearby beside the convex lens. We all know the formula. If we measure the image distance and the object distance, then we can find out the focal length. See the photograph. Here the setup. The mobile torch is used here as an object. Flashlight or a mobile torch, it is a very intense, so it can produce image very clearly on the screen. We are using it as an object, and using two clip, it can be placed here, kept here. There is a stand also. This is lens holder, and student can use to place the lens vertically. Other things means that they can use a clay or plasticine or moida, etc. Or they can use the clip also to place the convex lens. And here I have used a thick paper as a screen. It may be more transparent, etc. So particular object distance, we can find out the image distance. See the video first, and I have used a rule measuring tape to measure the object distance and image distance. This is the lens holder. When I have changed the position, we can see the size of the image is different. When it is the minimum, that is the particular image position, and we can find out the image distance. By changing the position of the screen or by changing the position of the lens or object, that is the mobile, we can fix the, we can find out the image position. For a particular image position, we just determine U and V, then we can find out the focal length. For different object distance, we can find out different image distance, and then we can make a graph 1 by V versus 1 by U, and from that graph, the intercept, we can calculate the focal length. And also it is better if we calculate the error incorporated in the experiment. I am coming to the next experiment, that is determination of focal length of a concave lens. But we know as convex lens produce real image, but to get the real image by concave lens, we have to combine a convex lens with the concave lens. I am coming to that experiment. Before that, I am showing another method to measuring the focal length of a convex lens, that is the displacement method. We know if the object and the screen is placed greater than the 4f. 4f means the focal length. Now already we have calculated the focal length of lens, convex lens, and so we will keep the screen greater than the 4f distance from the object, and then we can see that for two position of the lens, image will be produced, and so we can find out that two positions and the distance, that is the x. You can see here my lens is of focal length 10 centimeter and it is greater than 40 centimeter, the distance between the screen and the object. Here we can see another position of the image here, that is smaller. This is one position. This is the position. This is one position, and we can see the mark. Another position we can see here is the second position. If we measure this distance x, then we can calculate also the focal length, and we can verify with the previous value of the focal length. Now I am coming to the next, that is measuring the focal length of the concave lens. So we have to combine the concave lens with a convex lens, and we can find out the image position of the combined lens. By getting the image position, we can find out the focal length of the combined lens. If we know the combined lens focal length and the convex lens focal length is already known, so we can get the focal length of a concave lens. 1 by f equal to 1 by f1 plus 1 by f2, as here concave lens have focal length negative, so here I have put here negative sign. And so from this combination formula, we can find out the focal length of a concave lens. This is the setup, and here I have put two lenses using clips. You can do it, place it with another plasticine clay or etc. That is your expertization of the experiment. Here one convex lens and another is concave lens. For a particular position we can get the image, but there is another observation in this picture. By similar type like before, we can measure the object distance and the image distance, and from that the focal length. Another observation is that here you can see there is a arc in the picture, arc on the upper side. That is not due to the lens. Actually, this measuring tape have a curvature, and light coming from that, here image is producing. Now I am coming to the next experiment, that is to determine the refractive index of water.
Shomen, can I make a comment at this point? Just wait.
Yes, sir. Yes, sir.
Okay, you didn't mention the focal length of the concave lens that you have found and that of the convex lens. Can you mention that?
Yes, sir. Here I have I got the focal length of the convex lens was 10 centimeter, around 10 centimeter, and the combined lens around 20 centimeter.
And
So-
from that, what is the focal length of the concave lens coming to?
Concave lens is also 20 centimeter.
Okay, so now let us tell the students, here the focal length of the convex lens is less than the focal length of the concave lens, right? Focal length of the convex lens is 10 centimeter and that of the concave lens is 20 centimeter. Now the question is, why did we choose the focal lengths like that? If we had just taken the focal length of the convex lens of 20 centimeter and concave 10 centimeter, what do you think? We would have got the same convergent image and formed a real image? The answer is no. The physical reason is the power of a lens is the inverse of its focal length, you all know. So the focal length of the convex lens being 10 centimeters, it is more powerful than the concave lens. The idea is you'll have to combine two lenses to get the focal length of the concave lens with a more powerful convex lens than the concave one. So this is the most important point of designing this simple experiment. If you had done it other way around, you would never find a real image formed by the combination. Okay, so the physical idea is, I mean, the convex lens is trying to converge within a very short distance, whereas the concave is trying to diverge in a less angle. So overall system will be converged on a screen really, but if you do the other way around, the divergence is much more than convergence. So overall system will be diverged. So you won't get the real image. Therefore, in this combination, the convex lens should have more power or less focal length than the concave lens in order to find the real image formed on a screen. Okay? Okay. So, Showman, you can now
Okay, thank you, sir. Another thing is that when we combine these two lenses, it is better if we place the convex lens towards the object. Because if we place the convex lens first, then it will converge the light. But if we place the concave lens first, then it will diverge the light. Then it will not better for paraxial approximation, because the ray will be maybe the marginal also.
So the diverging light from the concave lens will fall on a greater area of the convex lens. So it will no longer be a paraxial approximation. Okay. That's
so
right.
it is better to place the convex lens towards the source. Okay, now we are going to the next experiment, that is to determine the refractive index of water by avoiding parallax. At first, what is parallax means? How can I avoid parallax? I request sir to discuss the parallax first, then I will go to the then experimental part.
Okay,
Sir.
so shall I?
I am
Can
stopping
you,
now.
uh,
I am
can
stopping
you-
now.
Okay, okay, all right. Okay, so now let me, in brief, give you the idea of parallax, and as Shomin was saying, how to avoid that. So maybe I don't know. Can you see my photo, or I will? It is a video actually. Can you see this?
No, sir.
Okay.
Till now.
You can't see.
No, I think you have to present first. Present your entire
Okay,
screen.
just a moment. Just a moment. Okay. So, okay, so, okay. Oh, I'll have to go to the meet and then I'll have to present. Okay, enter screen, then this one. Do I have to share?
Yes, share.
Okay, okay.
Yes, sir.
Yes,
now
sir.
it's
Now we
coming.
can.
Yeah, now it's
Okay. So now can everybody see the photo, or actually
yeah,
this
yes,
is
sir. Yes, yes.
okay. So let me first run the video and have a look. Okay. So what are you seeing? What I've done is I have put two pencils, one near to me, another further off, using two heavy books to press them, and I am moving my camera in the video mode. I am taking a video. So what you see, you are seeing the separation between the two objects is changing as I move my video. So the dictionary meaning of parallax is it is an apparent change in the position of an object when the observer changes position. Here the observer is my video camera, right? So as I move it across means if you draw a line connecting these two pencils, then my video motion is perpendicular to that. So this is across, okay? So let us see the video once again, but before that, let me tell that this shows the apparent position of each pencil is changing as a result of the movement of the video. So it is not the real position of the pencil is changing. It is the apparent change in position as a result of movement of the observer. So this is what is meant by parallax. Okay. So interesting point about this, that if you have two objects like here as two pencils, then the pencil that is nearer to you, that means nearer to the video camera, that will move faster, and the pencil that is farther off, that will move slower, and you can see the image at the back. Okay, so that will move even slower. See once again. Now try to understand. You see the first pencil is moving very fast. The second, sorry, I mean it stopped. Okay, so the second pencil is moving slower, and the third image is moving even slower. So this is a phenomenon of parallax, and this gives a very interesting observation that when there is a difference in distance between the two pencils, if you move your head across or the video camera across, the closer one will appear to move faster, and the distant one will appear to move slower. So this principle will be used by showmen to find out a real image. But before that, let me show you another video that is also important. This is what, I mean, I have focused on the two images of the pencils. I have taken my table lamp slightly at a different angle, show the images formed on the wall, and clearly we see two images. Now you see these two images are on the same wall. That's why they are at the same distance from me. Now, if they are at the same distance, then you will see that there is no relative separation. Just observe this video. There is no separation. I mean, no change in distance between the two images which are on the same wall, that is at the same distance. The pencil and the images, they are not moving. I am moving my video camera, or as you will be doing in your experiment, you will have to move your head So your change in position will give you an apparent shift in positions of the images. So if they are at the same distance, there will be no relative separation between the two images. So this is the basic idea of parallax. And so if you want to take these two pencils at the same position, what you'll have to do, you from your observations would know which one is moving faster. So you know that is closer to you. So the distant object, if that is the image formed by some convex lens, then you'll have to take the one which is closer to you and which is moving faster, close to this one by doing an experiment, or if you have something which is moving slower, then the other one has to be brought closer to this one, or you can move it to the other one. So this is the idea of parallax, by which we bring one object and its image at the same position. So this will be used in the focal length in the determination of refractive index of water. That will now be demonstrated by Showman. Okay, thank you. Showman, you can go ahead.
Okay, sir.
So,
Sir, please stop sharing.
okay, just a moment. Stop sharing.
So first go to the Google Meet, then start sharing. Meet, Google Meet.
Google Meet.
Google Meet.
Yeah, now stop presenting.
Stop presenting.
Okay.
Below.
Just a minute. Okay, so now stop presenting. Right? Sorry, I am not very.
No.
Okay, so we are presenting.
That stop presenting.
On the blue
It's
box.
coming in the blue on the blue box.
Oh,
Stop
okay.
presenting. Just a little bit above. Yeah.
Okay.
Now.
Sorry. Anyway, so Showman, you can go ahead now. Showman?
Yes, sir. I am now sharing.
Okay. All right.
Is it visible?
Not yet, sir. Yeah, now.
Excuse me, from VIC, I am Dr. Pratibha speaking. Can I ask one question? The participants appeared here. All of them understand Bengali? Can you ask this question? Can you ask this question from the name of the participants? If there is no objection, if using Bengali as the explaining language, then you can go to the mode of using Bengali. Na? I think
No, Pratibha, I think there are some participants from other states also, so it will be then difficult for them.
Okay.
No, but the point is,
but anyway,
for the larger part of the participants,
obviously.
If Bengali is more suitable, speakers.
If anyone has any objection, I don't want to.
Yeah, basically we can use also mixed language. It's not a problem.
I don't think it is a question of objection. Maybe speakers can say both Bengali and English. So
if anyone has difficulty in understanding Bengali, then okay, go. Let us continue with English. If it's not if there also no Bengali, then we can switch over to the Bengali, or we can use mixed mode of language.
Yeah, mixed mode of language would be more suitable, I think.
Okay.
Okay, so
my suggestion. Okay, thank you.
Okay,
okay, sir. So I am going to the mixed mode.
Yeah, okay, all right,
okay,
no problem.
Screen দেখা যাচ্ছে এখন? Visible now?
Yes.
আমরা প্যারালাক্স অ্যাভয়েড কি করে করতে হয় সেটা দেখলাম, যে পার্টিকুলার যখন যে দুটো পজিশন সেম একসাথে মুভ করবে তখন কিন্তু আমরা বুঝতে পারবো যে সেই পজিশনটাতে সেই ডিস্টেন্সটা সেম আছে। তো এই ক্ষেত্রে আরেকটা ভিডিও আমি দেখাচ্ছি, সেটাতেও একটা পেন, নিচে একটা পেন রাখা আছে, তার ইমেজটা, ওপরে একটা পেন, এরা যখন একসাথে মুভ করছে, ওপরে যদি আমি আমার মাথাটাকে নাড়াই তাহলে দেখতে পাবো যে দুটো একই সাথে মুভ করছে। কিন্তু আমি এই ওপরের পেনটাকে যদি একটু নিচে বা একটু উপরে তুলে নিই তাহলে কিন্তু তখন দেখবো যে এই দুটো, এই ব্লু রেড কালার এবং গ্রিন কালারের পেন দুটো যে টিপ দুটো নেওয়া হয়েছে এরা তখন আর একসাথে মুভ করবে না। একসাথে যদি মুভ না করে তাহলে বুঝবো তারা প্যারাল্যাক্স অ্যাভয়েড হয়নি, আর যদি একসাথে মুভ করে তাহলে বুঝবো প্যারাল্যাক্স অ্যাভয়েড হয়েছে। এই পদ্ধতিতে আমরা ইমেজের পজিশনটা বুঝতে চাই। নিচের পেনটার ইমেজটা যেখানে হয়েছে আমরা দেখতে পাবো সেই পার্টিকুলার যে পজিশনে এই দুটো একসাথে মুভ করবে তখন আমরা সেই পজিশনটাকে নেব ইমেজ পজিশন, এবং সেখান থেকে লেন্সের ডিস্টেন্স মেপে নিয়ে আমরা ইমেজ ডিস্টেন্সটা মেজার করব। তো এটার সাহায্যে আমরা রিফ্র্যাক্টিভ ইন্ডেক্স জলের কিভাবে বের করব, তার জন্য সেটআপ পিকচারটা এখানে দেখানো হয়েছে। খুব সহজে বাড়িতে বসেই এটা করা যাবে, এবং পুরো এক্সপেরিমেন্টাল সেটআপটার আইডিয়া সুরজিৎ স্যারের। এখানে এই একটা চেয়ারের হাতলের সাথে একটা স্কেলকে বোথ সাইড টেপ দিয়ে আটকে দেওয়া হয়েছে, এবং তার সাথে একটা ক্লিপ লাগানো আছে, যে ক্লিপটার সাথে একটা পেন বা কোনো রিফিল হতে পারে বা কোনো পেন্সিল হতে পারে যার মুখটা একটু সূচালো ইউজ করা হয়েছে। এরপর এখন কি হবে না, এই ক্লিপটাকে আমি ওপরে নিচে ওঠা নামাতে পারি সহজেই, যাতে করে আমি ইমেজের পজিশনটা কতটা উঁচুতে আছে বা নিচে আছে সহজে বুঝতে পারি। এখানে একটা বালতি, একটা বাকেট নেওয়া হয়েছে, যার তলাতে একটা স্কেল আছে, একদম তলায় একটা স্কেল রাখা আছে, যেটাও কিনা একটা বোথ সাইড টেপ দিয়ে আটকানো আছে, যাতে ওর উপর জল দিলে ওটা উঠে না চলে আসে। ওই স্কেলের কোনো একটা দাগকে আমরা এই পেনটার সাথে নেব, একসাথে মুভ করছে কিনা দেখব এই লেন্সের মধ্য দিয়ে। আর এই লেন্সটাকে বসানোর জন্য আর অন্য দুটো স্কেল রুলার নেওয়া হয়েছে, ওর মধ্য দিয়ে আমরা দেখব নিচের স্কেলটাকে। এটা পুরো ভিডিও আকারে একটু দেখাই। প্রসিডিওরটা নিচে একটা স্কেল রাখা হয়েছে, ওই যে নিচে স্কেলটা আছে সেটাও বোথ সাইড টেপ দিয়ে আটকানো হয়েছে, এই জন্যই যাতে করে জল দিলে আর উঠে না চলে আসে। বা এখানে আমরা যদি কোনো মেটাল স্কেল ইউজ করি তাহলে আর এটা আটকানোর দরকার হয় না, মেটাল স্কেলটার থেকে এটা দেখতে একটু সহজ হয়। কালো দাগগুলো, এক একটা দাগকে আমরা এখানে ব্যবহার করব ওই পেনের টিপটার সাথে একসাথে মুভ করছে কিনা দেখার জন্য। এর পরিবর্তে অন্য কোনো একটা ছুঁচ বা এই ধরনের কিছু রাখা যেত, কিন্তু এটাতে সুবিধা কি দাগ অনেক আছে, কোনো একটাকে আমি সহজেই নিতে পারি, এদিক ওদিক আমার সরানোর দরকার সহজে হবে না। এরপর বেশ কিছুটা জল দিয়ে দিলাম, জল দেওয়ার পর তার উপরে আমরা দুটো স্কেলকে রেখে তার উপর কোনো একটা ম্যাগনিফাইং গ্লাস বা লেন্স, এটা যেভাবে রাখলে আমার সুবিধা হবে তার মতো করে আমরা রাখবো, আর ওর মধ্য দিয়ে ওপর থেকে আমরা দেখবো স্কেলের দাগগুলোকে, আর এইখানে এই পেনের টিপ পয়েন্টটা এর সাথে কিভাবে হচ্ছে দেখবো। এটা খুব সহজেই কিন্তু ওপর নিচে ওঠানো নামানো যাবে এই ক্লিপটার সাহায্যে, যাতে করে আমরা ইমেজ ডিস্টেন্সটা পেতে পারি। এরপরে চলে আসি এখান থেকে আমরা কিভাবে
Showman,
refractive index
Sir, have you seen
Showman,
any
can I just
video?
make a comment here?
Sir,
Okay, you'll be just show the previous figure. আগের ছবিটা দেখাও।
হ্যাঁ, it is not coming now.
Okay, এটা হলেও হবে। So let me in brief tell you what's happening. Okay, so even if this figure is okay, all right. So okay, so this one.
Oh.
So Showman has kept a scale at the bottom of the bucket, and there is a convex lens. In this figure, it is just a magnifying glass I think, I mean, most of the household will be having magnifying glass, no problem, because there are old people in households. I mean, they generally prefer to read newspapers and things like that with this magnifying glass. So basically, this is a convex lens. So you know the focal length of this lens, and if the distance from the lens to the object at the bottom is greater than the focal length of the lens, then you can form a real image. For example, he is pouring some water, and you know the apparent depth of the object is different from the actual depth. So actual depth is from here to the bottom, and this one, what he has done is the apparent depth from the top of the water level to this position is the apparent depth. So you know this is a very interesting phenomena. For example, you go to a swimming pool, the depth you see is not the actual depth. So don't be too, I mean, courageous to get into that. Finding that this is too low, but not. It is not really low. I mean, actually, because of the apparent depth, it's looking very small, but its depth is higher than that. So you have to be very careful in swimming pools. Anyway, so the image of the apparent position, when the you are seeing this apparent position through the lens, the image will be formed on this side. If the position of the apparent position of the scale is greater than the focal length of the lens, then only a real image will be formed on this side. Okay, so that position you'll have to find using the pointer by avoiding the parallax. So this is the main idea of this experiment. Okay, Showman, you can go ahead now.
ওকে স্যার, সুতরাং এখানে এই স্কেলটাকে দেখে আমরা কোন পয়েন্টে দেখছি যে ওই স্কেলের কোনো একটা দাগের সাথে এই পয়েন্টটা একসাথে মুভ করছে, যে পয়েন্টটাতে এই পজিশনটাই হলো আমার কিনা ইমেজের পজিশন। এই ইমেজের পজিশন জেনে গেলে এখান থেকে লেন্স থেকে ওর ডিস্টেন্সটা আমরা স্কেল দিয়ে মেপে ভি পেয়ে যাব। আর এক্ষেত্রে আমাদের অবজেক্ট ডিস্টেন্সটা কিন্তু এই অ্যাপারেন্ট পজিশন যেটা স্কেলের, এই অ্যাপারেন্ট পজিশনটা লেন্স থেকে কত দূরে আছে সেই ডিস্টেন্সটা ইউ। তো এক্ষেত্রে আমরা রিয়েল ডেপথ কতটা মেজার করে নিয়েছি, বাকেটের হাইট কতটা মেজার করে নিয়েছি, সেখান থেকে আমাদের এই ডিস্টেন্সটা যদি আমি বাদ দিয়ে দিই তাহলেই আমার বাকিটা হয়ে যাবে অ্যাপারেন্ট ডেপথ, এই অংশটা অ্যাপারেন্ট ডেপথ। সুতরাং যখন আমার ভি জানা হয়ে গেল এবং লেন্সের ফোকাল লেন্থ আমরা জানি, সেখান থেকে ইউ ক্যালকুলেট করে নিতে পারবো। ইউ ক্যালকুলেশন হয়ে গেলে সেখান থেকে এই ডিস্টেন্সটা বাদ দিয়ে আমি অ্যাপারেন্ট ডেপথ পেয়ে যাচ্ছি। অ্যাপারেন্ট ডেপথ আমরা মেজার করতে পারলাম আর ডিটারমাইন করতে পারলাম, এবং রিয়েল ডেপথ আমরা মেজার করতে পারলাম। এই দুটোর রেশিও থেকে আমরা রিয়েল ডেপথ বাই অ্যাপারেন্ট ডেপথ করে জলের রিফ্র্যাক্টিভ ইন্ডেক্স বের করতে পারি। এরকম ডিফারেন্ট ওয়াটার লেভেল, জলের ওয়াটার লেভেলটা দুটো বা তিনটে ডিফারেন্ট ভ্যালুর জন্য আমরা আলাদা আলাদা করে রিফ্র্যাক্টিভ ইন্ডেক্স বের করব এবং তারপর একটা অ্যাভারেজ ভ্যালু নিতে হবে। এক্ষেত্রে লেন্সের ফোকাল লেন্থের উপর ডিপেন্ড করে এই বালতি হাইট কতটা হওয়া উচিত বা জলের হাইট কতটা হওয়া উচিত সেটা আমাদেরকে ভেবে নিতে হবে। না হলে এমন হতে পারে যে ইমেজের হাইট এত বেশি হলো সেটা হয়তো আমাকে কোনো একটা টুলের ওপর উঠে গিয়ে আমাকে ইমেজটা দেখতে হচ্ছে। তার জন্য যদি আমরা মোটামুটি 20 সেন্টিমিটার ফোকাল লেন্থের লেন্স ব্যবহার করি, বা এক্ষেত্রে আমাদের 10 সেন্টিমিটারের কনভেক্স লেন্স আর 20 সেন্টিমিটারের কনকেভ লেন্স, এই দুটোর কম্বিনেশন যদি ব্যবহার করি তাহলে সেটাও কম্বাইন্ড ফোকাল লেন্থটাও 20 সেন্টিমিটার হচ্ছে। সেক্ষেত্রে আমাদের বালতির হাইট হওয়া উচিত মোটামুটি 32 সেন্টিমিটার, 30 সেন্টিমিটার বা তার বেশি। 32 থেকে 35 এর মধ্যে বালতির হাইট যদি হয়, আমরা যে আমাদের যে হাইট তার মধ্যেই আমরা কিন্তু দেখতে পাবো। এবং সেক্ষেত্রে জলের হাইট আমরা 5 সেন্টিমিটার, 10 সেন্টিমিটার বা 15 সেন্টিমিটার নিতে পারি। যদি শুধুমাত্র কনভেক্স লেন্স নিয়ে করি আমরা, এবং সেই কনভেক্স লেন্সের ফোকাল লেন্থ আমাদের কাছে যেটা আছে সেটা যদি 10 সেন্টিমিটার এরকম কম হয়, সেক্ষেত্রে আমাকে বালতির হাইটটা নিতে হবে একটু ছোট, 27 বা 25 সেন্টিমিটার এরকম কম হাইটের যদি বালতি পাওয়া যায়, সেটা নিয়ে কাজ করলে আমরা এটা পাবো। আদারওয়াইজ কি হবে, বেশি হাইটের নিলে এই বিভিন্ন ওয়াটার হাইটের জন্য যে চেঞ্জটা ইমেজের, সেটা খুব একটা বেশি হবে না। একটা ভ্যালু মেজার করার জন্য কোনো সমস্যা নেই, যখন 2-3টে ভ্যালু আমরা মেজার করতে যাব তখন ওই ভি এর চেঞ্জটা খুব একটা বেশি পাবো না। তো এইভাবে আমরা দুটো বা তিনটে জলের হাইটের জন্য রিফ্র্যাক্টিভ ইন্ডেক্স আমরা বের করে তার একটা অ্যাভারেজ ভ্যালু বের করতে পারি। থ্যাংক ইউ। যদি কারো কোনো কোশ্চেন থাকে তাহলে করতে পারো।
Thank you, sir, for your nice presentation. And this is really interesting. I think now at least students get an idea that even at their home, they can basically make a physics lab like their colleges with the easily accessible devices. So, is there any question, Shubhenduda?
No questions.
Okay, let me check the YouTube live. No, there is no question. So thank you, sir. Maybe the students will surely get back to you once they will try it. And now we are moving to the third technical.
So I will upload this paper, this presentation in the Google Classroom today night.
Okay, yeah, you upload it in the Google Drive, so they can download it from there.
Okay.
Thank you, sir.
Okay, thank you.
So now we are moving to the last technical session of today. Dr. Surojit Chakravarti, sir, he will explain you again some experiments which can be done at home using lenses. So you can start now.
Okay, so now I am sharing my screen. So hide this one. Okay. So can you see my title page?
Yes, sir. Yes, sir.
Okay. So now I will discuss a very simple experiment, but it yields a very interesting result. That is determination of the refractive index and radius of curvature of an equiconvex lens using the lens as a concave mirror. So the last part is very important. I will be using the lens as a concave mirror. So let's see how it goes around. Okay. So these are the things that Showman has already discussed. That is, the focal length of the lens is given by this formula 1 by V 1 minus 1 by U with mu minus 1 into 1 by R1 minus 1 by R2. If you fiddle around with this equation, you come to the expression of F is equal to R by 2 into mu minus 1. Here I have assumed that R1, R2, the two radii of curvature of the two surfaces are equal in magnitude. Since one is in the one direction, the other radius of curvature is in the other direction, they have a relative minus sign. So this term becomes positive. I mean, so this sign becomes plus. And so you get 2 by R, where R is equal to R1 is equal to R2 is equal to R. That is we are assuming that this is an equiconvex lens. The two surfaces have the same radius. So when it becomes plus, it becomes 2 by R, and you have the relationship F is equal to R divided by 2 into mu minus 1. Now our aim in this experiment is to find mu and R both. What happens in college is you measure the focal length of the lens and you measure the radius of curvature of this equiconvex lens by the spherometer. Now the problem is you don't have a spherometer at home. So how do you get this mu and R separately? So for that you need a different equation. So you will have two equations and two unknowns like mu and R, and you can determine both. So for getting this other equation, we have arranged a thing like this, where I'll have to explain the schematic by this photograph. What is this? O is, I think you can see this figure, right? Dr. Dashgupta, can
Yes, yeah. Your screen is visible.
Okay. So
Yeah.
it needs a bit of explaining. So I have an object here, and the rays that form a real image on the other side of the lens, that is formed by transmission through the lens. Okay. Now we know the reflection coefficient of light on glass of, say, refractive index 1.5 is about 4 or 5%. And this comes out from Maxwell's equation, and probably the first year and second year, they have not yet studied, but you just take it for granted that the reflection coefficient is very small in class. But it has some reflection property. So we have used the reflection property of this concave surface. With respect to this object, this one is a concave surface. So the image reflected from this can be held on a paper, or is a real image. And this can be done if we have a sufficiently strong source of light. That is the most important thing. Even if this reflection coefficient is about 5%, that means the total energy of light that is falling here, about 96% is getting transmitted. That's why you get the image on this other side, real image, so easily. That is what Showman has described so far. But the reflection coefficient being so small, generally we don't see this image formed on the same side of the lens as the object. So if you have a source of sufficient strength, you can see this image. That is the key to this, to the solution of this. Here I am using the lens as a concave mirror and seeing the image formed on the same side of the object as the source of my light is strong. Once again, we use the torch of a mobile phone. So you see, mobile phone is coming all the time and doing an experiment from home. So since the light is pretty strong, the light reflected from this concave surface is forming a real image. But the other surface, that is convex, that doesn't form a real image by reflection. That's why we are saved. We are not bothered about this convex surface. It can't form a real image on this side. Real image can be formed only by a concave surface. By reflection, you are getting the real image. So if you have the relationship between the object distance of O from the center of this lens and the image distance, which I call V here, and object distance is U here, if you can measure this relationship, I will show you a photograph how these have been measured by Showman. So from these two measurements, we can find the focal length of the mirror. But this focal length will not be the same as the focal length you are used to for a concave mirror, because you have with this concave mirror, there is some refractive media which actually converges the image to a closer distance, since the you can see from the figure that this image is formed. So the relationship between the object and image distance and the focal length of this mirror will be somewhat different, but in form it is the equation of a mirror that I will come to. So now let me give you the experimental observation. This is the once again Showman's experiment. I have borrowed from his work. Actually, we both have worked on this and actually published a paper in Physics Education Journal, prestigious journal published from UK. So I am giving the photograph from that paper. So what is this? This is the source of light. That is essentially the torch light of the mobile. Then once again, you have the convex lens held in a stand. Even if you don't have stand, don't have a stand, I mean, you can make this convex lens stand erect by using clips, as Showman has shown in previous experiments. So that is not a problem. So all you need in this experiment, a mobile phone that all of you must be having, or maybe most of you will be having. Then if you can have a convex lens, it is never more than about 80 or 90 rupees. If you can, or most of the households will be having one magnifying glass. So you can try with that. And you note a chart paper, a strong, thick chart paper on which to hold the image. That also you put up like that with a clip, and you'll have to have a tape measure of say 3 meter or 5 meter. There are all sorts of measures available. So if you have one, you are, I mean, you have all the elements that you can do this interesting experiment. Okay, so the object distance is from the mobile phone to the lens, and the image distance is from the image position to the lens. These two, this is U and this is V. Okay, so now if you ask me, how are you sure that this is not the reflection of the front surface? That I have already explained. That is a convex one, so that can't give a real image like that. So it must be due to the concave surface at the back, which is forming this image. So this is a very well focused position. And so let me show you a video which will explain you how to focus that. So this is the video. Let me run it. So this is also a Showman's work. So I'm borrowing his video, so you can see, I mean, how he is focusing. It's very simple. The minimum dimension when you arrive, that is the focal position. So, okay. Okay, thank you, Showman. Okay, so you know how to focus, and when you get a good focus, then you have the image distance here, and there is the object distance. Now the question is how to get the relationship between the object distance and image distance and the focal length of this concave mirror, which we get from the lens itself. So I won't give you, I mean, go into the details of mathematics. These are already uploaded in the Google Classroom. So I'll just give you the concept. So what we did with this, you see, this process is consisting of 3 steps. First one is refraction at the first surface, which separates the medium air with refractive index 1 with refractive index mu on the other side. So this is the first step. Second step is reflection from the concave part. And third is this reflected image getting once again refracted at the first surface. So now this refraction is happening from the refracting from a medium of refractive index mu to 1. The previous one, the first one was from 1 to mu. So now from mu to 1, and the second step is the reflection. So these are the 3 steps you'll have to form your mathematics with. So the first step is this. This is what is known as the Gauss's relation. This is not exactly the lens equation. This is the relationship between object and image distance u and v2 for refraction at a single surface. Now you massage this equation that I'm not going into. So this is the first equation for refraction at the first surface. Now this is the second equation, the standard reflection formula from a concave surface. If you have an object distance v2, image distance v3, then the focal length is r by 2. So 1 by v3 plus 1 by v2 is equal to 2 by r2. R2 because actually the reflection is occurring from the second surface, which is appearing as a concave one. So once again, some massaging of this equation, I'm not going into that. That is there in my note, details note. And the third step is once again the refraction from inside the medium of refractive index mu to outside of refractive index 1. So now one comes in before and the other is this, and this is the number equation number 8 is the third equation for the refraction at the second surface when light is coming from inside to outside. Now you have 3 equations and 2 virtual positions that so this is the virtual position V3 and the virtual position V2. So our aim is to eliminate these 2 things because we can find out the distances of these virtual positions. So what we will do with these 3 equations, we'll eliminate the virtual positions and we'll be left with the equation of the focal length of the lens that is given by this relationship. 1 by v plus 1 is this quantity, or 1. So you can see now this is once again a reflection equation from a curved surface, but now the focal length is not r by 2, but it is something different. So that is given here. 1 by fm is equal to this. So the magnitude of the focal length is given by this equation. So you have the second equation that we are trying to get. So now you have fm, that is the focal length of the lens when it is used as a concave mirror. So this is the important concept that is there in this work. So fm is there of this value, and f we already got in the very first slide. And if you get the ratio f by fm, you get this relationship. So you have measured f, you have measured fm, because both you can hold on a screen, so you can measure the distance from the lens. And that's how you can measure you can calculate the focal lengths of the lens and the concave mirror of the lens used as a concave mirror. So if you measure these 2 things, you can calculate mu, and if you know mu, you can calculate the radius of curvature as we showed earlier. If you know mu, you know f, you can calculate r. So without the use of a spherometer, you can calculate these things very easily from home. All you need is a lens, and all other things are easily available. Most of you have this smartphone and a tape measure, and so if you can arrange for a lens, you can very easily measure mu and r. There are other ways, of course, of measuring r without using spherometer. I mean, if somebody later on from our resource persons tell it, they can tell it. There are other methods. By measuring the diameter of the lens and measuring the thickness of the lens also, you can find the radius of curvature. So that if somebody finds time, we'll tell you how to do that. So you see, I mean, if you have a lens, you can just play around with it and find a number of things. For example, I can suggest you something else. For example, if you have a lens of known focal length, if somebody asks you, what is the height of your room? Most of you will not probably able to give a very exact result, or I mean, a result within say 2-3 millimeters accuracy. Now, if you have a lens of focal length known, then you can easily find it out. You place your mobile phone with its torch on the floor. Then put the lens of the focal length that you know on the, I mean, now this light will be falling on the ceiling, and you'll see a large blob of lighted area. Okay, so now if you place your lens with your hand onto the beam of light and you change the position of your lens up and down, you can really focus it on the ceiling, and that means the size of this light spot will be minimum. So that tells you that it is really focused. So when it is focused, you can ask somebody, some of your friend or anybody in your family to measure the distance of the lens from the cell phone. If you have that, you have actually and you know the focal length of the lens, so you can calculate V. That means the height of the ceiling from the lens. You can easily find out the V. So the total height of your ceiling will be U plus V in magnitude. So you calculate, if you do the error calculation, you can see that the error will not be more than 2-3 millimeters. If you can really measure the height of the lens from the mobile phone with some 2-3 millimeters accuracy. Okay, so this tells you, and these are fun experiments. I mean, you can do this at home. I mean, I think at least I got a real pleasure in finding the height of my room so simply with this, without using any tape or anything, just by using the convex lens that I have with me. It is essentially my hand magnifier. I don't have a lens as Showman is using. So with that, I could measure my height of the room. Okay, so I am through. I am finished. So if any of you have any questions, you can ask.
Yes, thank you, sir. Thank you, sir, very much. Shubhenduda?
Now one question
Is there
has
any
been
question?
arise, one question from Jayashree Mondal. What is the maximum distance between lens and the source?
Sorry?
What is the maximum distance can I use from the lens from the source?
Okay. So you see, there is a minimum distance, first of all. You can't come closer than the focal length of the lens for forming a real image, right? Now, you are asking about maximum distance. Now, if you have ever, if you plot U and V, you will see that it is almost like a rectangular hyperbola, U versus V. So if you increase your object distance U, the V becomes very small. So, I mean, you'll have to make a compromise up to what distance you can go for your object. For example, obviously, you can put your object in this particular experiment or some other to a very large distance of 5 meters or things like that. Then the image will be formed at such a small distance, you will not be able to measure the distance from the lens accurately. Similarly, obviously, closer you can't go for more than the focal length, because then there will be no real image formation. So there is a limitation. But if you go on increasing, then the measurement of the image distance becomes impracticable and error prone. So you'll have to make a compromise and get U and V both measurable with very little error. So I hope that gives answer to your question.
Thank you.
Any other questions, or
I think just you can understand.
Joyashree Mondal? Okay. I think she has got answer. So,
Yeah.
Dr.
Okay,
Dashgupta, so we have,
yes,
and
we have come to the end of the first day.
actually,
And
Bhupathi sir was asking something. Bhupathi, can you?
So first of all, I have checked. It appears Professor Das has not been able to come join. I mean, he said that he will try to join, say, close to 8 o'clock, but it appears he has not been able to make himself free. So that way, he is not here. So what should be our next step?
Well, our time is still 8, right? So we have still about 10 or 15 minutes. So
I can
Yes,
present my experiment, which I'm supposed to present tomorrow, because it's a small one. I can describe it.
So if you can finish maybe with 5 minutes more, you can. So I don't know. I mean,
yeah, there is no problem. Yes, no problem,
Okay.
sir.
Okay.
But Shuri sir, you have to stop presenting. Stop
Okay.
presenting.
Okay. Just a minute. Once again.
Yeah, that blue box.
Okay. Thank you.
So should I go ahead with my presentation?
Yes, sir.
Yes, sir.
Okay. I'm going to share my screen, but before that, a brief introduction. I hope all the students know from their common experience, it's an everyday experience, so to speak. If you really try to cool down something, any hot, maybe a cup of tea, maybe a bowl full of rice, whatever it is, we find that initially it takes time. I mean, it becomes colder pretty soon. It loses heat pretty at a faster rate. But when the temperature becomes more and more close to the surrounding temperature, it loses heat at a slower rate. It's a common experience. I mean, you need not take any measurement, but we know from common experience. Even the hot tea remains warm for a long time, though it doesn't remain hot. The point is that one can understand as a student of physics that if we really want to draw a time temperature graph of this phenomenon, this cooling phenomenon, this is definitely not going to be a linear graph because the cooling really does not take place uniformly. Now, quite often, as I told in my last experiment also, we do try to make some linear graph, even if by adjusting or suitably choosing the parameters, because all of us know that it is much more convenient to draw a linear graph. In fact, in the last experiment, it has already been described by one of the presenters that if you draw 1 by v and versus 1 by u graph, you will get a straight line. So that way it's more convenient with the lesser number of points. But with a graph that is not linear, we need more number of points. Now, what I am really going to suggest that let us draw a very simple thing, first a cooling curve. And of course, we can do beyond that. That is something I shall explain from my screen sharing, and let me go for that. It appears it is not coming. Why not? I don't understand. I mean, apparently it came up to this point that has got stuck up. Should
Sir,
I
your
go out and
screen
try
is
again?
visible, but your Google Meet screen is visible.
Should I go out and try again?
Yes, you can do that.
Okay, let me do that. Okay. Yeah, I mean, I don't know why it is not coming. Is it coming?
Yeah, it's now we can see you.
Can you
Desktop,
see?
yes.
Can
Yeah,
you
the
say?
desktop, yes.
Can you see this?
Yeah, yes.
Okay. No,
Few
no, no.
videos and I think few
Not,
videos
not,
are there.
not this one. Let me try it. Yeah. I think I will
Yes.
get it.
Yeah.
Okay, let me do it. Now you see, basically, if we really collect data on the time and temperature, we shall come up with a graph like this. If temperature here I put this diagram from normally I have used theta, but t has been written there. This is a time temperature graph. The graph comes out to be like this. This much we know. In a way, this is straightforward. Now we quite often talk about Newton's law of cooling, which tells us when the surrounding temperature is not very large, the difference between the surrounding temperature and the hot body is not very large, then the rate of cooling is linear. I mean, rate of cooling is proportional to the temperature. Temperature means the average temperature. Now, if we can really do one thing, if we can draw after getting this graph is straightforward. You will have to get this graph, but there are some issues. For example, initially, since the temperature fall will be larger, you will have to take the readings at a shorter interval, but later on you may like to change this interval. 2-3 points are there. that if try to use, suppose you have taken some hot water in a bowl, take some larger amount of water so that it takes time to cool off and so that you can take the readings comfortably. If you take the hot water in a small cup, then it will cool down pretty fast. And one more thing is that keep the environment uniform. By this I mean, if you have really kept it in such a position where no fan is switched on, you keep that position. Or if you really keep it in a position where the fan is running on, well, you keep that position. So it's better you try to ensure that same cooling environment is present so that it can cool with. This cooling is not being affected. All along being affected by the surrounding uniformly. So we get a graph like this. Now the most interesting part is this, which I'd like to. That's what I have chosen this experiment to talk about. Now we want to have, ultimately our objective is to have a d theta versus t graph. That means rate of cooling versus time graph. Now as you can see, normally what we do, we need to draw tangent to this graph at different points, different time, so that we can get the d theta dt at different points and that versus time. Suppose this is the time, I go up, this is the time, and find out the d theta dt. The question is how to find out the d theta dt. Quite often, our students always use this. We also instruct them to do that because that is something that's prescribed in the experiment. There's Lee's method experiment where we get this type of cooling graph, and we choose some of the ways like counting small squares or really we draw tangents over here. But there is definitely a better way. I'm going to explain that. In fact, I would like the students to try out this one. Basically, you will have to collect the data and try to draw a smooth graph as far as possible. By smooth graph, you can understand naturally the graph will not pass through all the points as it happened here, but the graph is smooth. You can use suitable sticks or suitable narrow sticks. Sometimes people use, there are flexi graphs available. So you draw a smooth graph. Then let us do this thing. Now, once we have got this graph, you can see this is the graph. Now, suppose I want to draw the tangent at this point. Whatever way you take your approach, it's going to be hugely wrong if you really try to draw a line over here. Instead of doing that, let us take a small piece of mirror. You will find them in the photo binding shops in your locality where the photo framers, they frame the photographs. They use these small pieces of mirror, something like 4 inches by 4 inches, even 4 inches by 3 inches will do, 10 cm by 10 cm, roughly. This is just to give you an idea. Now, if you really hold that piece of mirror vertically over this line, you will find that I really didn't mark it. The back side, this is the front side. Towards my right is the front side, left side is, silver. Now, if you really put it over there, you will find the reflection of this part of the graph in the mirror. And if you will find it is getting broken up as if there are two different graphs. But if you can orient this graph properly, this mirror properly, a time will come, you will find the graph looks completely smooth. That means the original graph and its reflected graph, as if they are joined smoothly. That ensures that this particular mirror has been placed normally at this point. So what will happen? This will happen like this. I had one more diagram, sorry. Okay. What will happen? It will really, you can really put it like this. Let me just check. I had one more diagram. If I don't get it, I shall come back here. No. Sorry. I don't think I have. Anyway, look at this graph. Look at this mirror. Now this mirror, if you really put up one dot here and one dot here, you will get the normal to this graph at this point. So if you get the normal of the graph at this point, you will really be able to find out the tangent, because tangent is having a slope -1 by m. Just please allow me to check. I believe I am having that. Just let me go back over here and just try. Let me try it out. Just see. Let me have a look. I believe I did it, but I don't get it now. Sorry, just did I keep it here? I don't know. Well, I don't know where I kept it. Anyway, just uh, if this particular line is given the normal, as you can understand, once the graph is smoothly reflected in this mirror is locating the position of the normal at this point. So if you put two dots and draw a line, you will get the normal, slope of the normal. If you calculate it, you will get the slope of the normal, which if it is m minus 1 by m will give you the uh, tangent at this point. So if you want to get the d theta dt at this point, you can do it in this way only. Now suppose you bring it here, then there is another position. Then once again you do the same exercise. Look at the graph and the reflection of the graph and see whether they look smoothly. By orienting the mirror, you will have to rotate it about this point, and if a time will come, you will find the reflected line and the original graph, they look smooth. So once again, this particular position of the mirror gives us the position of the normal to the graph at this point. Once again, we calculate the slope of the normal by graph from the graph, taking delta y by delta x. Here it is delta theta by delta t, and that will give us the slope of the normal, and by taking minus 1 by m, we shall get the slope of the slope of the tangent. So that way, we need to really find out the different values from here, and naturally, once we have done this, this is a particular time, this is a particular time. After doing all these things, we can really plot d theta dt versus t graph, and you will get it as a straight line. And moreover, if you can really plot d theta dt versus theta graph, which really gives us the Newton's law of cooling. D theta dt is proportional to theta. You can draw d theta dt versus theta graph because this is one value of theta, this is another value of theta. So that way you can draw that graph, and it is expected to be a straight line with a negative slope, of course. And this is a straightforward experiment. You need to use, of course, a digital thermometer. Digital thermometer is about 150, 175 rupees. It is available. But if you have a digital thermometer at your disposal, you can do a number of experiments with the help of that instrument. So it's like this. Let me sum up. You take some hot water in a bowl, a little bit more amount of hot water. Hot water means, say, it may be at 80, 90 degrees Celsius. And then you start taking the reading. The digital thermometers is normally having one long rod as the sensor. You put it inside water, and there is one digital display that will give you the temperature, and you use your watch, or the stopwatch in your mobile phone to get the time, and you go on recording it from time to time. And as I told you initially, you take at a faster interval. Interval should be smaller at a faster rate because cooling down takes place at a faster rate. Then, of course, you can really slow down a bit because with the same interval of time, the temperature will not fall down to that extent. Once you have taken all this data, you plot this graph, and then use this small piece of mirror and see what you are getting. This is going to be a new exercise for you. You can see the drawing the tangent is not at all easy on a card. It becomes quite often it becomes erroneous. You draw it this way, your friend will draw it in a different way, and everybody will argue, no, this is the best tangent. But if you really go for this one, you will get the tangent at that point in a very convenient way. So this is an exercise which will help you to do certain experiments in your curriculum. And moreover, if you really learn this particular thing of drawing tangent on a curved surface, that may be useful for other experiments also. So I think I should stop here, and of course I'm ready to address any question. So what I shall do, I shall stop sharing and go back to the original screen.
Yes, thank you very much, sir. Shubhanuda, any question?
No question.
Okay, so I think we have to give them some time so that once only, they will do it by their own hand, then only they will have the queries. So I want to thank all the speakers. In spite of their busy schedule, they gave us some time and explained in a very interesting and also very detailed and lucid way that how we can think of the experiments we usually do in our practical classes in a very standard method. But there are certain different methods, alternative methods, through which also we can do these experiments without the loss of any accuracy of the result. And if students and also us, if we try these experiments, maybe we will understand physics in a better way, because maybe the ideas are sometimes seems like it's very simple, but once we really want to do the experiment, then we find some difficulties and we have to then revisit our knowledge or revise our knowledge, whether we understood the things really well or not. And then we may come up with some new ideas or better understanding. So I request, or maybe I hope that the students will at least try some of the experiments which they are learning here. So apart from their syllabus. So that's a standard way they do it in their practical science classes. They have to give the exams, but it's not like that. It's just to learn physics, just to understand in a better way. You please try it by yourself. So once you have your result, we will make the WhatsApp group, or maybe also we can add you in a Google Classroom, so we can put your results, we can put your queries. So please stay tuned for these 3 days, and then hopefully it will be a very successful one, and you will get some advantage of this workshop. Okay, I think one question came up, Bhupathi sir, by Oyan Raj. Shubhendu, can you please read out the question?
Oyan Raj made a question. There the graph did not touch 3 points.
Well, this is experiment.
The reason.
This is not theory. It is very likely even more points may not touch the graph. You will have to draw the mean graph. That means you will really give due weightage or due respect to all the data points you have collected, unless you feel that one is very wide off the mark and maybe rejected. Then you give respect to all the data points and then draw a mean graph. And when we talk about the mean graph, it is expected some of the points will lie above the line, some of the points will lie below the line. Don't try to draw the line, I mean, even if it's a curve or a straight line, whatever it is, to all the points, because ultimately we need to have for a straight line graph, we need to have a straight line. For a curved one, we need to have a smooth curve. It's not that, I mean, in weather reports, you may find that there are bumpy curves because they join point to point to describe the day-to-day temperature. But it's a phenomenon, physical phenomenon, where this curve is expected to be a smooth one. So in experimental physics, you will have this. So this is the characteristic, I must say. Don't get disheartened. This is the characteristic of experimental physics.
এমনিতে কখনো শুনেছি যে লিস্ট স্কয়ার মেথডটা একটু বুঝিয়ে দিলে হয় গ্রাফ আঁকার সম্বন্ধে।
সরি,
যদি মনে করেন লিস্ট স্কয়ার মেথডটা বুঝিয়ে দিলে পারেন। আজকে না, পরে কখনো।
আচ্ছা, আসলে মানে এরা তো একদম এলিমেন্টারি, মানে এরা আমার তো ক্লাসেও এক্সপেরিমেন্ট করেনি।
যখন কনভিনিয়েন্ট হবে।
There is one, I mean the same person, Oyan Raj, is asking one question, I mean the part of the question. Can you repeat this question?
Yes, please tell again about the position of the mirror. মানে মিররের পজিশন সম্বন্ধে একটু জানতে চাইছি, ওই যে আপনি মিররের কথাটা বলুন।
আচ্ছা, মিররটা এমন ভাবে হোল্ড করতে হবে যাতে করে মিররের সামনে দিকে গ্রাফের যে অংশটা আছে কার্ভ গ্রাফের, আর মিররে রিফ্লেক্টেড যে অংশটা হচ্ছে, এই দুটো একটা স্মুথ গ্রাফের মতো দেখায়। অর্থাৎ মিররটা একটু সেই পয়েন্টে ধরে অল্প বিস্তর ঘোরালে দেখা যাবে the graph, original graph before the mirror and its reflection that is formed as an image that is formed through reflection, they appear as a smooth one. That will ensure that mirror has been placed as a normal at that point. So if we give two dots at the two ends of the mirror and then take out the mirror and draw a straight line, তাহলে আমি ওই পয়েন্টে নরমালটা পেয়ে যাব। নরমালটা পেয়ে গেলে তার থেকে আমি নরমালের স্লোপ পরবর্তীতে ট্যানজেন্টের স্লোপ বাড়াবো।
এটা একটা ইউনিক ওয়ে অফ ডুইং দ্য ট্যানজেন্ট। আমরা লিজ মেথড করতাম এবং সেখানে খুব অসুবিধে হতো। ডক্টর চক্রবর্তী যে মেথডটা বলেছেন সেটা কিন্তু অসাধারণ। মানে এটা
মানে incidentally এটা কিন্তু I'd like to stress this point. This is widely used in, say, in Mumbai. I know in all Mumbai colleges people use this. Somehow or other we could not adopt this. I learned it from there only.
না, আমি আগের কথা যেটা সুরজিৎদাকে বলছিলাম যে ওই যে ভূপতি যে ওয়েদার গ্রাফ সেখানে ওই বাম্প দেখায় কারণ পয়েন্ট টু পয়েন্ট জয়েন করে, সেটা তো ঠিক গ্রাফ আঁকা নয়, সেটা সর্ট অফ কি
Data
বলবো,
presentation, data
হ্যাঁ
presentation.
ডেটা প্রেজেন্টেশন। গ্রাফ আঁকতে গেলে মিন গ্রাফ, সেটা কোনো একটা কনভিনিয়েন্ট সময়, আমি আজকে ইজ ডেফিনেটলি দ্য রং টাইম, কোনো একটা কনভিনিয়েন্ট সময় লিস্ট স্কোয়ার মেথডটা সম্পর্কে এদের অন্তত সেন্সিটাইজ করে দিলে আমার মনে হয় ভালো হয়।
সেটা হতেই পারে, কিন্তু আমাদের প্রোগ্রাম কিন্তু খুব প্যাক শিডিউল, আর মানে এগুলো তো আমার ধারণা ওরা ক্লাসেই শিখবে, মানে সেটা মানে যদি দরকার লাগে।
Since this discussion has come up, I would like to point out one thing. Chinmoy, Dr. Ghosh, আমার মনে হয় লিস্ট স্কোয়ার মেথডটা তো আমাকে থিওরিটিক্যালি বেস গ্রাফ বলতে শেখাচ্ছে, সেটা একটা নিশ্চয়ই তার গুরুত্ব একরকম, কিন্তু আমি চাইবো যে আমরা দরকার পড়লে কিছু ডেটা ছেলেরা জেনারেট করুক এক্সপেরিমেন্ট থেকে, সেখানে শিখুক কোনটা বাদ দিয়ে, হয়তো 10টা পয়েন্ট নিয়েছে, দরকার পড়লে 2টো বাদ দিয়ে রাখলে ভালো হয়। এইগুলো আগে শিখলে পরে আমার মনে হয় ভালো। থিওরিটিক্যালি বেস পয়েন্টটা করতে গেলে কিন্তু গ্রাফ আঁকাটা আবার হবে না। আমি গ্রাফ আঁকাটাই
না, কিন্তু 2টো পয়েন্ট বাদ দেবে কিসের ভিত্তিতে?
কিসের ভিত্তিতে এটাই দেবে, ওর কনসিস্টেন্সি হচ্ছে, ওর ডেটার কনসিস্টেন্সি হচ্ছে। যদি 8টা পয়েন্ট দিয়ে মেইন গ্রাফটা খুব ভালো হয়, তাহলে ওটাকে আমি বলবো ওর বেস্ট গ্রাফ। কেননা এমন হতে পারে বাকি 2টো পয়েন্ট দিয়ে হয়তো রেজাল্টটা বেস্ট পাওয়া যেত, কিন্তু ওর ডেটা থেকে মোস্ট কনসিস্টেন্ট হচ্ছে সেটাই।
দেখা যাক, আমরা আমাদের রেগুলার শিডিউলে যা আছে সেটা দেখি কিরকম যায় আর আগামী 2 দিন, দেন উইল ডিসাইড অ্যান্ড লেটস সি, মানে উই ক্যান হ্যাভ এ ডিসকাশন, মানে কি করে আরো 2 দিন তো টক আছে, দেখা যাক।
হ্যাঁ, থ্যাংক ইউ। হ্যাঁ, ঠিক আছে।
ঠিক আছে।
So I thank you all for being here for the last almost 2 hours and 10 minutes. So hope to see you again tomorrow sharp at 4 p.m. And I also must thank again the members of IMPT for conducting this workshop. And I want to thank also my departmental colleagues as well as our principal madam. Thank you all. See you tomorrow.
Thank you, Dr. Dasgupta. Thank you.
Good night.
Good night.
Yes, I also thank the speakers also, resource persons.
Thank you. Good night.
Yeah, participants may leave now. আর আমাদের যদি একটু কথা থাকে আমরা ঠিক থাকতে পারি, যেটা যেরকম বলবেন।
একটু কথা আছে তো রে।
ঠিক আছে প্রতিভাদি, তাহলে আমরা একটু থেকে যাই।